These are notes for section 5.2, verifying trigonometric identities. This is probably the hardest part of this course, but the whole purpose behind this is so that students continue to get practice with the trigonometric identities, which need to be memorized. And also that you get the process of verifying using steps. The person reading through the process must be able to follow the sequence of steps that the student is doing. There are different techniques. The easiest method is usually just substitution, and I'll show you examples of each of these techniques. Another technique is to factor, and there are different levels of factoring, and these are important. So this is the second thing I tend to look for, and I'll show you when. Sometimes if you have fractions, getting a common denominator will help you through the process. And so what we're going to be doing with this process is we're going to be working on one side of the equation. I tend to set these up where the more complicated side is the left side and the more simplified version is the right. So I will most of the time ask you to work on the left side of the equation until it equals the right side. We're going to draw a vertical dashed line through the equal sign to separate the left side from the right side. And each step must be a valid mathematical step. These are not going to be proofs like you think of in geometry. I want you to write the reason for the step on one side of the vertical dashed line, but it does not have to, it's not a formal proof. The reason I want you to write what's on the right hand side, your reason for your steps, is so you get to go through the process and you think out loud of what you're doing. And then I encourage you, if you make a mistake, don't erase it. Cross out your work and start again. There really might be something valid in what you've started, and I want to see the process that you're going through. And if you're not sure what to do, start by just using substitution. It may be clear to you when you see it. My first example is I have cotangent x, sine x is equal to cosine x. My first step is I'm just going to use plain substitution. So cotangent x I know is cosine x over sine x. The reason I choose the substitution is because I'm always looking on the right hand side to see what I want to get to. I want to get to cosine x. So if I change cotangent to cosine x over sine x, that's going to lead me to a cosine x. When I multiply fractions, I multiply numerator times numerator, denominator times denominator. So what I've got here, cosine x times sine x over sine x. Then when you simplify fractions, if you have sine x over sine x, that's equal to 1. So I reduce the fraction and I get cosine x. I'm putting a lot more detail on the right hand side in the parentheses. That is more for me to explain to you or for you to look back for notes. But I don't expect you to do all that. I expect you to write just what's here: quotient identity, multiply fractions, and reduce fractions. My next example secant theta times cosine negative theta minus sine squared theta equals cosine squared theta. This one, if I did some simple substitution, it may work, but I'm looking at, first of all, my substitution is going to be cosine negative theta is going to be replaced with cosine theta. And that's an even-odd identity. Then I replace secant theta with 1 over cosine theta. And I've done this several times, so I know where I'm going with this. It's harder to see it, but the next step I think should make it a little bit easier to see. Cosine theta over cosine theta is going to equal 1. So when I multiply the fractions, I replace cosine theta over cosine theta with 1. Then I've got a Pythagorean identity. Pythagorean identity gets used frequently with these. So I replace 1 with sine squared theta plus cosine squared theta. This is where it gets easier to see. If you want to get to cosine squared theta, you have to introduce cosine squared somewhere. And this is where I can do it. Sine squared theta and a negative sine squared theta is going to equal 0. So this leaves me with just cosine theta. So if sine squared minus sine squared is 0, and now that identity is done. My next identity, this is one that we don't use that often, so students tend to struggle with. It's the cofunction identity. Anytime you see pi over 2 minus x or pi over 2 minus theta, you're probably going to use a cofunction identity. So the first step I'm going to do is I'm going to replace sine pi over 2 minus x with cosine x. And I use a cofunction identity. After you've done these for a few times, you could do 2 steps in one, because the next step I'm replacing cosine pi over 2 minus x with sine x. And that's just another cofunction identity. Now I have cosine x over sine x. And that's a quotient identity, which becomes cotangent x. And that's what I wanted to end up with. So these first 3 examples use substitution. Here's my 4th example. I have sine theta over tangent theta plus cosine theta over cotangent theta on the left-hand side, and sine theta plus cosine theta on the right-hand side. So it looks like I need to get rid of the fraction and get rid of tangent and cotangent. The way I'm going to do that, first of all, I'm going to use a quotient identity, and I replace tangent theta with sine theta over cosine theta, and cotangent theta with cosine theta over sine theta. Now I've got a lot of fractions going on, and this is one thing students tend to struggle with, not because of the trig, but because of the fractions. When you divide by a fraction, you take the fraction that's in the denominator, you flip it, and you multiply. My example over here on the right is showing that with numbers. So 3 divided by 2/5 is going to equal 3 times 5 over 2. Flip the second fraction and multiply. So that's what I've done here. Now when I multiply, sine theta times cosine theta over sine theta reduces just to cosine theta. And notice as I go further into this, I take less steps. In a formal proof, you cannot skip these steps. That's why I say these are not proofs. Cosine theta times sine theta over cosine theta is just going to equal sine theta. So I multiply and simplify. This is the same thing, but I just rearranged it to get to the exact same answer. So sine theta plus cosine theta, and I just rearranged it. So once again, not a formal proof. My next example now will be the first example with factoring. I've got secant x minus secant x times sine squared x is equal to cosine x. Since I have a secant x in both terms, I'm going to go ahead and factor out the greatest common factor, which is secant x. When I factor out a secant x, I'm left with 1 minus sine squared x. Don't forget, when you're factoring, if there's a minus sign up here, there has to be a minus sign here. Double check by multiplying secant x times 1 and secant x multiplied by negative sine squared x. Then, like I did in the previous problem on example 3, I could go ahead and replace the 1 with sine squared x plus cosine squared x. The reason I'm doing that is because I know I want to end up with a cosine x. And if I introduce this sine squared plus cosine squared, I'm going to have a sine squared and a negative sine squared, and that's going to be 0. So that's my next step. I simplified it and got to secant x multiplied cosine squared x. Since I want to end up with cosine x, my next step is to take secant x and make it 1 over cosine x using the reciprocal identity. When I multiply these two fractions, I get cosine squared x over cosine x, and that will reduce to cosine x. two more examples. The first example, I have cosine to the fourth of theta minus sine to the fourth theta. And I want it to equal 1 minus sine squared theta. This is going to be factoring, but this factoring is a difference of squares. So I get cosine squared theta minus sine squared theta, and then cosine squared theta plus sine squared theta. Cosine squared theta plus sine squared theta is equal to 1 from the Pythagorean identity. So when I replace that with 1, I'm left with cosine squared minus sine squared. And I look to where I want to go. I want to go to 1 minus 2 sine squared theta. So I want to get rid of the cosine squared theta. Well, if you notice, if you rearrange the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. I could get and solve this for cosine squared, and I get 1 minus sine squared theta. So I come back over here and I replace cosine squared theta with 1 minus sine squared theta. I'm one step away. When I combine like terms, 1 minus sine squared theta minus sine squared theta ends up being 1 minus 2 sine squared theta, and that is what I wanted to end up with. So that one is done. My last example has more steps going on. And it's got a fraction. So this is one where I'm going to have some more work with fractions. I have sine x over 1 plus cosine x plus 1 plus cosine x over sine x is equal to 2 cosecant x. So what I'm thinking of here is if I want to end up with 2 cosecant x, I want to end up with 2 over sine x. So I'm going to get a common denominator. My first fraction, sine x over 1 plus cosine x, I'm going to multiply by sine x over sine x. My second fraction, 1 plus cosine x over sine x, I'm going to multiply by 1 plus cosine x over 1 plus cosine x. And then when I multiply, numerator times numerator gives me sine squared x. My denominator I'm not going to multiply together, and you'll see why in a minute. My numerator on the second fraction, 1 plus cosine x times 1 plus cosine x, will be 1 plus cosine x squared. And my denominator I'm not going to multiply. When I'm adding fractions, I add the numerators and the denominators stay the same. So I have sine squared x plus 1 plus cosine x squared. Denominator stays the same. This is where you're going to have to be careful. When I multiply 1 plus cosine x times 1 plus cosine x, it's a binomial. Over here on the right hand side I show you how I did it. 1 plus cosine x, 1 plus cosine x. Multiply the first terms, the outside, the inside, and the last terms. So that's where I get 1 plus 2 cosine x plus cosine squared x. Then I can use the Pythagorean identity. I'm going to replace sine squared x plus cosine squared x with 1. So that's where I get this one. Then I have the other one, plus 2 cosine x. And notice I'm writing my denominator each time, but I'm not multiplying it. I add the 1 and the 1 together to get 2, so I have 2 plus 2 cosine x. And this is where I keep every step I look back at what I want to get to. I want to get to 2 cosecant x. So I've got the 2. I don't have cosecant, but I have a sine here in the denominator, so 1 over sine is going to give me cosecant. So my next step is going to be to factor the 2. That's my greatest common factor. So I have 2, 1 plus cosine x over 1 plus cosine x times sine x. the 1 plus cosine x here and the 1 plus cosine x here going to reduce to 1. So I have 2 over sine x. And then I'm one step away. I can split this fraction apart. And some of you will see this without having to split it apart. But the 2 is going to be multiplied by 1 over sine x. I replace 1 over sine x with cosecant x. And each time I'm giving my reasons here. Your reasons don't have to be exactly the same. The process doesn't have to be exactly the same. There can be multiple ways to do these. These are just examples to help you follow the process.